day 2, COD Summit, super exciting, and I have a fun talk for you, and it's going to be on secure COD. So we heard an introduction of security in COD yesterday from some of our talks, and you might have even heard some words like TEE, security, and MPC. So we're going to get more into that today. So first, the definition of secret COD. Secret COD is very liberally defined as the ability to run computation over data in a way that is admissible to all parties so that they all trust it. So this is in comparison to definitions like must be encrypted. So the talk title was originally Encrypted COD, but that doesn't really make much sense because it rules out things like secure multi-party computation, zero knowledge, and those. So this is really a flexible definition that includes what I'm about to talk about. Oh, thank you. Okay, perfect. So secret COD is really useful to all of us because it allows us to do things with data that we have not been able to do before, including using secrets within these special environments that allow you to do finance, for instance, using API keys to talk to Binance, like MPC, government use cases because they don't want to share data in between government agencies. And my favorite, which is going to be personalized AI, trained and inferenced on your own personal data. So that's really what I'm going for with this, but all of these other things are things that we care about in the interim. And this is a slide from one of our partner projects called MetaMirror, and they're tackling decentralized advertising, which is a giant industry, and it's dependent on secure COD because the data is private, and because of regulations like GDPR and just overall sentiment, you can no longer get access to those strong tracking signals from the devices. So you have to re-implement them, but in a privacy-preserving way, hence secure COD. So the goal I told you about earlier was the AI training, and there's a whole blog post on it. I won't get into that, but this is a relatively speculative blog post. It's based on this is essentially the culmination of 6 years of work I've been doing research on distributed secure computing. I built this thing a few times, so like I kind of know all the failure modes. So this is like not going to be the failure mode. And so we have Web4, the autonomous web, which is going to be my vision of the web of secure agents, like autonomous AI agents, protected from the outside world through the use of secure COD. So you have these independent autonomous agents securely running with their own personalities, their own instructions, on off-chain private data, using the on-chain world for consensus and state of the world. But we'll get into that more. So the rest of the talk is going to be a demo. I'm going to explain a core building block of how I am approaching secure COD, and then some other stuff which is like a little bit more like out there and somewhat of a commentary on the Lilypad APIs that I was using but had to migrate off of. And then the final framework that I'm building. So first a demo, because demos are fun. This is NF Trout. This is a game that I've been building that is the world's first autonomous breeding game. So it's like CryptoKitties, but sorry, I can't breathe. Okay, so it's exactly like CryptoKitties, except the seeds, the genes, are actually private. So if CryptoKitties, you might remember, is centralized, the breeding is done on the centralized servers owned by CryptoKitties. In this case, it's being done distributed, and nobody knows the genes. So here's just the general workflow. You select a trout, you select another trout, MetaMask pops up, you breed, and now you have the trout incubating. At this point, Bacalhau pops up, does the computation, returns the results to the chain, and you have a new trout. So this is being done within a trusted environment, such that nobody, not even me, can see what genes the trout has. All right, so that was a fun demo. Oh, well, am I pointing at the screen there? So now here's the underlying way that we do this. So the technology is called trusted execution environments, and we're going to get into that now. So trusted execution environments are one of the different ways you can provide privacy to programs. So other ways you can do it are zero knowledge, secure MPC, federated learning, and fully homomorphic encryption. So of these, the most interesting to me are like fully homomorphic encryption, secure multi-party computation, and of course trusted execution. I love federation, but it's not really as general purpose as the rest. And then in terms of the comparisons, trusted execution environments, despite having particular trust assumptions in that you must trust the hardware manufacturer, you must trust that people don't do this like bad thing that costs a lot of money to the TE and break it, you get a lot of flexibility and performance if you can tolerate those or work around them. But then if you need that SMPC and FHE, they still exist. They're really nice. but they don't have that same kind of performance and flexibility. All right, so now TEE, in more detail, is a secure mode of your processor that allows you to do encrypted computation without even the server admin knowing what's going on, because the way it does this is it interposes on the memory bus to encrypt all signals going into and out of the processor. So you get memory encryption, you get the registers are essentially encrypted, and then also you get the ability to prove that your particular hardware enclave, as they're called, is running a particular piece of software. So it can assign a cryptographic attestation of being a particular piece of software. So if you remember back from my autonomous agent thing, this is kind of interesting because these agents can cryptographically attest using trusted hardware that they are a particular agent, so you gain this sort of computational identity. So now if you remember from 2 slides ago, over here you see that trust level is moderate for TEE. So why am I saying that? If you have a TEE in a data center, it is expensive. Like, it costs like $100,000 or so to like put one of these giant scanning electron microscopes, like with a focused ion beam, into your data center and extract the secret keys from your TEE. So it's not cheap. Certainly not cheap, but it's also not like exorbitantly expensive. You can be targeted by like a state level actor or something like that. So if you're running truly confidential workloads like AI-based finance or just regular finance even, anything that deals with personal data, then you're going to want to take some defensive measures. So in the blockchain community, we have these networks like Oasis Network, Secret, Obscuro. They're layer 1s based on this TEE technology. And a common complaint of those is that TEE is terrible, there are leaks, there are bugs that can expose the keys, and of course, like, this is very bad for these layer 1s that are just replicating their keys, their secrets, and everything across the decentralized network, and they don't have those trust assumptions. So instead what we're doing is routing computation to trust. So the key point behind that is trust as a resource. So in the same way that you have like your Bacalhau nodes scheduled based on how many CPUs you have, how many GPUs you have this other resource that is trust. So everyone, when they're born, has some trust assumptions, and over time they grow different ones. And it can end up with like wildly varying perspectives, like I trust Amazon, I don't trust AliCloud, and those kinds of things. But they're unique to each person. It's hard for a platform, especially a layer 1, to pop up and decide that like I can support everything, because really it can't. So it has to focus on that lowest common denominator, the lowest trust entity, and build for that, which is extremely inconvenient and not what we're trying to do here. So we're trying to make this go back to like basics and make life easy for people based on existing trust assumptions. All right, so this next component is going to be a little bit different. It's not about the hardware or trust, but it's how we then go and use these fundamental primitives of security to offer a good developer experience and a good autonomous agent experience. I'm calling that computational diversity inclusion because, well, you'll see. So the main point of this is a task-based execution system. So if you're familiar with Lilypad, the idea is you take a job, you request the job gets scheduled, and a node comes over and picks it up. So it's a good model, but it's what I have encountered several times in the past that wasn't optimally scalable. And the reason why it doesn't scale so well is because blockchains are not good at dispatch. They're really good at verification. So you have like ZK rollups doing verification on blockchain, like all these sorts of different algorithms, and like so it makes more sense for the smart contract to simply verify the task results, store that state of the world. At the root of the consensus mechanism, right, it's just like a root hash. So they're all just doing consensus over the state of the world. So by eschewing these opinionated and inflexible and gas inefficient dispatch frameworks on chain and simply moving to a, if it works, then I accept the results, then you can use that to maintain whatever root of trust or whatever state root on chain that you want based on your particular trust model. So here's what the API looks like, if you can see it. It's just super simple. Like, all you do is this a good task? Like, do I accept these task results? And if you do, then you update the state of the world. So the contract doesn't even need to know what tasks it even has. So if you remember back from the NF trout example in the very beginning, each trout is a task. The contract doesn't know how many trouts exist. An infinite number could exist, but scheduling all of those would be, like, of course, cost prohibitive. So whenever a node pops up and says, so once the contract mints a new trout, or a new trout is minted by a user, it creates a state of imbalance in the universe, meaning that a task has been created. So a worker running off-chain can pick up the task, see that it needs to be completed, figure out how to compute it on its own. That's the key part. It has to do all of the work. It's not encoded on-chain unless you specifically put that there, and then completes it, getting a reward or some other thing. But it doesn't really matter. All that the contract has to do is say, I accept or I do not accept. And then the data that goes in there is, probably point at it. Oh, well, I can't point. Anyway, the proof in the report. So this can capture a very wide variety of verification mechanisms, including TEE, zero knowledge, and just trusted sender, for instance, if you have a permission deployment. So this API is pretty flexible. It doesn't really do anything, but at the same time, it provides a very interesting base layer for things that can be built on top of it. And that those things that can be built on top of it are policies. So the task acceptor that you see here is an acceptance policy. It changes what you see on chain. And if anything gets accepted, that changes the global state of the world, and that's consensus. Now, there are two steps, though. One is the task acceptance is at the very final end. And at the very beginning of when you want to complete a task, you have what's known as a key policy. A key policy is running on a key policy network like lit network backed by whatever, like let's say Solana, Ethereum. And when you can authenticate to the key policy network, it will release a key to whomever is trusted. So if you're using trusted execution environments, you can require the key policy, which looks almost entirely like the task acceptance policy, to do a TEE attestation verification according to the root certificate of the hardware manufacturer, for instance, Intel, and then release the key to that attested enclave such that you have high assurance that the enclave is not leaking the secrets. And of course, you can also have higher order requirements such as geographic location and contractual agreement through, for instance, KYC, using this same interface, which is just the verification interface. So the contracts only do verification for tasks and keys. So we put this all together into this system that I'm calling Escrin. It means box in Old French. And it basically is a runtime that it's an executor for Bacalhau or similarly architected platforms that you just put your functions, you put your data in, it will do the attestation for you using decentralized attestation networks. So we're using Oasis Network for that. And it will also do the key management such that you can do things like random number generation, key derivation, encryption, signing, all with the security inside these enclaves such that the hardware operator can't see what's going on. So it really allows you to make these autonomous systems. And here's that's the back way. Okay, so here is this a big complicated diagram that just shows you the overall steps. Like I won't get too much into it, but like at the very core is this executor, or the runtime, which of course is like this Bacalhau, Bacalhau runs this. So this is like, for instance, workerd. We're using the Cloudflare workerd. You can also use things like Wasm time, or well, really anything. But like Wasm is really headed for the moon, I suppose. And then of course you have these off-chain policies, on-chain policies, and different sources of data. So in the same way that IPVM is very flexible, this is intended to be very flexible because it's so very hard to be opinionated in this decentralized data space. Okay, so the future work is going to be on creating policies, actually upstreaming this into Bacalhau, and just overall getting development on the platform, because I think that secure computing is really a public good and something that we're just trying to make happen in the world. So this is a nonprofit. A lot of us here do nonprofit stuff, public good, open source. So here's just a bunch of links for how to get involved. You probably are just looking at it, not going to click. So I have this QR code for the exact link to this slide. So then you can then go to view the slides in your free time. All right, and then that's everything from the deck, and I appreciate your time for listening to this. Thank you for attending, and I hope you have a good rest of the conference. If you have any questions, then happy to answer them. Thanks, everyone.